Okay, so for Cambridge 2.4, question 8a we'll start with. Because the complex number is root 3 plus I, you can see hopefully that is close to the exact values that we want, being root 3 on 2 and 1 on 2. So the trick here is to actually put in what you want, which is root 3 on 2 plus 1 on 2i, and to compensate for the fact that we've just put in a factor of 2 in the denominator, we need to put 2 at the front in the numerator. Now the reason that's beneficial, because 2 becomes the modulus sitting out the front there, and we just need to use our exact value triangles to figure out that we've got 1, 2 and root 3 here. And root 3 on 2 is cos of pi on 3 goes there, and pi on 6 goes here. So for cos, root 3 on 2 is pi on 6, and sine of 1 on 2 is pi on 6, which means our argument is pi on 6. So we can write this in the form of 2 cos pi on 6 plus I sine pi on 6, which means we've now got it in mod arg form. And so that's equal to 2 cis pi on 6. Now, using Demoivre's theorem, finding square roots is really as simple as doing what we would normally do, take the power and apply it to the things, and because a square root is the power of a half, you take the modulus and you do it to the power of a half, and that is obviously just equal to root 2, and you take the argument and you halve it. So the argument is equal to half of pi on 6, which is just pi on 12. And so one of the roots for this is going to be root 2 cis pi on 12, and that one is the first root, but we've got to find 1 to get the other root, and because they're square roots, it should be hopefully fairly obvious that they've just got to be plus and minus, because it's the same number, plus minus with square roots, and so you should get plus and minus root 2 cis pi on 12. Okay, in part B, we've got we're cube rooting minus 2i, and this is another complex number. Again, we're always trying to put it back into exact values. Now, there's no root 3s, and there's no 2s, excuse me. So that looks a lot like 45 degrees, because the magnitude of both numbers is minus 2, and therefore it looks like it's 45 degrees. So what I want for 45 degrees is I need 1 over root 2, and that, in order to get 1 over root 2, I need to factorise out actually 2 root 2. And because I want my modulus to be positive, I make that minus 1 on root 2, and I make that minus 1 on root 2, and I. Okay, so again, the reason I get 2 root 2 out the front there is because 1 on root 2 is what I want as a magnitude. I need it to be negative on the inside, because I can't have my modulus being negative, because it's just a length. And so I'm left with a common argument there. Okay, my modulus is out the front there, and you can write that as a root if you like So the other option for writing that is root 8 outside of minus 1 on root 2, minus 1 on root 2i. Okay, so that number is in the third quadrant because it's minus and minus. In the first quadrant, that would be 45 degrees as we said, but because it's in the third quadrant, you're looking at this scenario here, where it would be 45 degrees if it was in an exact value triangle, but because it's in the third quadrant, you've got negative 3 pi on 4. I should say up here pi on 4 as well, rather than 45 degrees. Okay, so you've got your argument, you've got your modulus, and in order to use de Moivre's theorem, you just need to use those two things. So, at that point in time, what we want to do is use de Moivre's theorem and cube roots. And in order to use cube roots, we need to understand what multiplies by itself 3 times to give root 8. And that is root 2, because root 2 times root 2 times root 2 equals root 8. So, the modulus is equal to root 8 to the power of a third, which is equal to root 2. So that one's not too hard. The argument, on the other hand, is a little more complex because we need obviously an argument that is a third of that one. So minus pi on 4 is one of them, but the question is, how do we find then the other ones? So the straight up argument is 1/3 times 3 pi on 4. So that's the first one, which gives us an argument of pi on 4. But we need the other arguments also. And so to find the other arguments, you can use your geometrical spacing principle to find where they are around. So if we get, sorry, that should be minus pi on 4 there, because that's minus 3 pi on 4. Sorry. And so the geometrical spacing is, you got minus pi on 4 there, and then the other two roots are equally spaced, and so they are going to be at an angle of 360 divided by 3 is 120, which is 2 pi on 3. So they're going to be roughly there and there, I suppose. And so the second two arguments should be minus pi on 4 plus 2 pi on 3, which is this one up here, and the other one should be, and the third argument should be minus pi on 4 minus 2 pi on 3, which is this one over here. And all you need to do there is to just, add the two fractions, and you get here 8 pi on 12 minus 3 pi on 12 for the first one. So that is 5 pi on 12. And here you get minus 3 pi on 12 minus 8 pi on 12, which is minus 11 pi on 12. And so your three roots then become, because they all have the same modulus, you have root 2 cis minus pi on 4, which was the original one we found, root 2 cis 5 pi on 12 for the second one, and for the third one, root 2 cis minus 11 pi on 12. And that should be it.